Thank you very much. Good morning, and I realize I stand between you and lunch, so I'll do my best. I'd like to thank my co-authors, acknowledge them, Allan Legge, who's in the room over there, and Doug Maynard from the Canadian Forest Service. They are the two really long-term science advisors that have participated for over 10 years with our members on these technical committees and were instrumental in getting us to where we are today. I'd like to start by giving you just a little bit of chronology. Forest monitoring in the network sense has actually been going on in the Athabasca oil sands region since 1997. So in 1998, WBA measured above and below ground parameters on a regional network of 10 jack pine stands. Jack pine was chosen as the ecotype because acid deposition was very much the issue back then, and these sandy, dry soils are the most sensitive to acid deposition. It was decided to repeat this exercise on a 6-year cycle, and so in 2004, the organization once again sampled above and below ground, this time on an expanded network of 13 plots, 8 of which were measured in 1998, and there was 1 plot added kind of in between the two 6-year cycles. However, in 2006-07, I referred to this yesterday, a science panel reviewed the existing monitoring program based on the 2004 results. And this was a panel of external authorities plus science advisors mixed in with WBA members. And in 2008 to 11, the network was significantly enhanced and expanded with a significant increase in funding. And so this gets us to 2011, when the third in the 6-year cycles, this happened to be 7. We had to lapse a year, but this is the third cycle of measurement, and that's really the main thrust of this talk. Some of the key findings from the 1998 and 2004 surveys are these. Yes, there was accumulation of some heavy metals, sulfur, nitrogen, in lichens, vegetation, and mineral soils at plots that were within 30 kilometers of the large upgrading mining sources. However, there were no significant changes in 1998 to 2004 in some of the key soil properties like pH and cation exchange capacity. Did not see any change in tree condition and did not measure any change in tree productivity. And you can see there one of the reports that was produced by Suzanne Visser on the ectomycorrhizae soil biology. So over a 3 or 4 year period in preparation for the next survey, which took place in 2011, as I said, there were a lot of changes made. Number one, we opted to adopt the source to sink measurement approach. So we wanted to follow and take measurements at key points along the air pollution pathway from emissions right through to deposition, accumulation, processing by the receptors. We adopted the forest health approach, which is all about the resilience of the system, not so much the anthropocentric measurements of radial diameter or tree growth. We wanted to know more about how the system is actually functioning, and if there is a change, what is the degree of resilience? How might it behave in the future? Could we predict that? We went away from the categorical approach of stratifying plots in high deposition zones and low deposition zones. That really limited our ability to deal with the issue of hormesis, where we know that systems are under stress. You always have a positive stimulation before you see the negative response. We didn't have plots in that middle deposition zone, so we might have had things happening out here compared to the reference plots, but didn't have the right array of plots in the middle to allow us to get that response curve. We expanded the plot network. We went from 13 to 25, and then, as you'll see with the edge plots, 50 plots. And we used the ecological analogous site approach. We also was very clear we wanted to measure inputs, so inputs being interannual climate, deposition, and we wanted to measure responses, the indicators, endpoints, and we wanted to do them in space and time in the same places. You see there in that photograph, that is the typical jack pine plot in our network now. That's the Analogue type 3. It's a very open jack pine canopy, understory dominated by Cladina lichen with some Archistaphylos. One key driver, and we spent 3 years doing this, is Dr. Legge's 25-year project in Whitecourt, studying strong sulfur point sources, sour gas plant, proved that the ecological analog approach was the way to go. What it does for you is it significantly reduces the noise within the plot and between plot. It absolutely maximizes the opportunity that you have to detect a pollutant signal if it's there. And so we put a lot of effort over 3 years in finding 200 candidate ecological analogous plots. We ended up going with type 3, which is the soils are very poor and they're some of the most xeric sites. Again, being most sensitive. This is the array that we have now. There are 25 internal jack pine stand plots. They extend out 150 kilometers in all directions. We also added 24 edge plots to give us this early warning capacity. We want to measure those every 3 years so that we don't find ourselves in a situation with tree condition changing and we're kind of behind, we're playing catch up. We have 6 30-meter solar-powered meteorological towers out there bracketing the region. One north, one east, one west, 2 south, and 1 in the main plume path going west to east. We have 23 passive monitoring towers, which allow us to get some measure of pollutant exposure. Because there is no power, there's only one of these plots we actually can drive to. We have to fly by helicopter to all the rest. We have 3 portable ozone monitors now that run on solar and give us continuing ozone data because we're concerned about ozone, and we can move these around by heli. And we also have plant root simulators, which we use to give us some sense of the soil ion movement. And you can see probably on this map, although not very well, at many of these plots, say 213 in Saskatchewan, you'll see there's about 4 or 5 different things happening at the same plot. This is the plot layout. Where possible, we try to find stands that have an exposed edge. It may be a fen, a bog, or whatever, and we try to orient the plots so they're facing the main industry sources. So we're getting the maximum exposure we think possible, and therefore getting the signal if it's coming that way. We have 1 vegetation plot in there. We have 5 different soil plots that we sample on this 6-year cycle. And you can see scattered around there we have in the open little mini towers. Here you see one of the solar towers on the left, the solar panels on our separate tower. We now have continuous hourly MET data streaming by satellite or cell modem uplink every day to our database. And this is data I think would be very useful for people working in aquatics, biodiversity, and we're happy to make all that available, and it will be publicly very shortly for anyone to use. You see on the right one of our edge plots, so we'd be sampling the jack pine at the edge there, and we have the little mini towers where we measure passive pollutant and climate using the solar-powered systems. These are the indicators that we measure on a 6-year cycle. We have a range of vegetation indicators, plant community characteristics, species diversity, tree productivity. We look at internode length, we look at needle retention, We sample off-plot trees for a whole range of macro, minor elements, trace elements. We also use cuticle wax chemistry, which is probably the best early warning signal of change. Soils, we do pretty much a lot of the routine analyses, pH, cation exchange capacity, total carbon, nitrogen, sulfur, and so on. We also use lichens as a sensitive biomonitor, so we look at community composition. We use them as biomonitoring sponges. And we integrated this all together. We also do use a lot of our forest health plots for our source receptor modeling work, and so that we have isotopic analysis done in the through-fall deposition, in the soils, in plant root simulators for lead, mercury, and other isotopes. This allows us to really determine, in cumulative effects sense, what sources types are adding what amounts to each of these plots. So in 2011, as I've said, we had a cruise of about 5 or 6 or more university scientists out for a period of 4 weeks, flying in helicopters to take all the samples. So what did we find? We're issuing this report very shortly. It's just in the desktop publishing stage. Our members have done their review of it, and the revisions have been made, so that should be made public very shortly. The authors of the report are, as you see, Sean Watmai helped us out with critical loads, Keith Puckett did the lichens and so on, Sue Grayston as a Canada Research Chair in soil biology. So it was a joint effort to put together the 12 chapters. In the report you will see spatial maps of pollutant exposure for a number of years. This is the reactive nitrogen kriging. We'll be reporting the pollutant trends previous to the intensive harvest. Measured deposition, we use these ion exchange resins both in the open and in the through-fall under the tree canopy. And if you look at the left column and the right column, you'll see that essentially the through-fall deposition, especially very close into the sources, is about twice as high as the deposition we measure in the open. And so the point here is that if 40% of the landscape is forested and has dense tree canopies like trembling aspen, if you're just using the open measurements, you're going to underestimate the total deposition to the landscape by maybe 100%. The predominant mechanism of deposition in the region is, of course, dry deposition. So what we're seeing here is the particulate being retained by the canopy and washed out in rain events. We see the typical patterns in lichens that we've seen in all of our work, decreasing concentrations as you move away from the sources, the mine edges or the upgraders. We see some change. JP 104 is 13 kilometers from two of the upgraders. So in a few of the plots, we see that sulfur concentrations in the jack pine needles is increasing over time. Others it isn't. We have a couple of plots where 104, 212, again close to the operators, where we see an increase in nitrogen retention by the needles. Interestingly, some of the work Sue's done, she's been able to sort and group our 25 plots by various sort of principal component type analysis, and they do segregate with some degree of sense. Also in the report, we have some new CalPUF dispersion model runs. You can see here sulfur on the left and nitrogen on the left for both the lower Athabasca region and also accounting for the 1 or 2 kilograms that is coming in to the region from south of us. We also have new maps for base cation deposition and potential acid input. This is all to inform us that are trying to interpret the vegetation soils data as to what the deposition actually was, so that we can make appropriate conclusions. So getting on to the findings, just got 2 or 3 more slides to go. What are the main findings from the 2011 survey? We don't see any abiotic disease insect incidence, no increase in it. There are no significant relationships between tree productivity and deposition. We don't see any negative evidence of effects of acidification on the understory plant community. This may be due to the base cation deposition, which we're seeing that may be offsetting that. We don't see any increase in grasses or forbs at the highest deposition sites, and that's something we would expect to see if we were having a high nitrogen load. We see an increased total and vascular plant species richness in the understory, but that may be partly an artifact of some other things. But we do think that base cation input may be having a bit of a fertilizing effect. Soils, we do see some changes in soil parameters within 20 kilometers of the major sources. We do see sulfur building up or accumulating in the soils. However, the nitrogen seems to be being taken up by the vegetation. It's not accumulating in the soil, whereas the sulfur is being conserved. In terms of management frameworks, one of our duties is to report the base cation aluminum ratio. It's a trigger for Alberta, and I can just report that the trigger was not exceeded in 2011. Critical loads calculations, we think that the risk of soil acidification and adverse biological effects is actually relatively low now. However, if there's a decrease in base cation deposition, perhaps that risk will increase. And we think that the risk of adverse effects due to nitrogen deposition is currently greater than that due to acid deposition. So conclusions, the state of the forest health, as best we can determine, is good, as measured more than 13, 14 kilometers away from the strong point sources and mines. 13 kilometers is the operative word here. Those of us that have worked all over the Northern Hemisphere around strong point sources, whether they be smelters or coal-fired power plants, pulp mills, one always sees trees and forests under stress within a number of kilometers of strong sources. That's just a given. We do have evidence of loading and accumulation of some pollutants, and we are reporting now that base cation deposition is playing, at least hitherto, a rather unreported role in the overall functioning and dynamics of this system. We think there's a potential to harmonize WB and Legge monitoring frequency. Turns out we're both working on basically the same ecotype, but we're doing it at different cycles and different frequencies, and we think we should just get together and so that we can look at the whole land use region together. Some new data came to me the other day, and I was a little astounded. Turns out that 43% of the NOx emissions in the airshed are actually south of Fort McMurray in the in situ operations, and those are expected to continue to grow. We are currently deficient in forest health monitoring. We've mainly been focusing on the north, and so we need to put an effort into beefing up the system south of McMurray. And as always, one of my main messages is we absolutely have to have continuity in monitoring to look at these very long-term, particularly cumulative effects. So thank you very much.